Hi everyone. In this brief example, I'm talking about natural joins. So the notation for natural joins is R with the join notation to relation S. And this is going to be where we want to select things from multiple relations that also require cross product or multiple Cartesian products from that as well. So remember, a cross product is where we take an outcome from the R times the S of two relations, and we get a bunch of more products from there. What simplifies this a bit further is that we're also going to add a type of selection operation into there. And this kind of does it naturally for us, hence natural join, where we don't need to specify what exactly to select. So for the full definition, we could say that R and S be relations on schemas R and S respectively. Then R natural join to relation S is relation on schema R union of S obtained as follows. Each pair of tuples from R and each pair of tuple from S, once they're considered, if they have the same value on each of the attributes, so essentially the rows are identical, add a tuple T to the result, where T is the same value as T R on the relation R, and T is the same value in TS on the relation S. Now, if there isn't the same result, we'll have to get a little different with what we do here, but we can go through a brief example that's given to you in the slides. So you could see here that if I have my relation R and a relation S, I have my 4 attributes here and 3 attributes in my relation S. And what I'm going to say is join R on relation S here. We could see here when I look at my very first one, I could say, okay, so I have A in my attribute A, my B in this one, they're both 1. My C column is the alpha still, and there's none in there. My D column is still A right here. There's none in this one. Sorry. The D column in both of these are the same. And then E isn't inside of this one, so we can just append it there. So from this natural join that we have with these two, we could say now A1A and then, or alpha 1, alpha A, and alpha. Okay. So if I have a relation R with ABCD and a relation S with EBD, our resulting schema here, we bring in A from our first one. We bring in B because it's common in both of them. We bring in C because it's in our first one. D, it's common in both of them. And then we have to append in the attribute of E at the end of there to result for it. Cool. So to continue a bit more with these types of joints, when we were looking at R and S alone, it might have looked a bit more confusing. But essentially, if we are asked questions like find all the instructors in a computer science department together with their course titles and all that they teach, we can essentially state, okay, join instructor and teaches and course on a specific selection. And we want to make sure that that selection that we're joining on is where the department name is equal to computer science. Okay, so in this attribute here, so what we might be able to say, all the courses of comp sci, sorry about that. So it says project name and title from the relation, that's the join of instructor, teaches, and course. And remember, this is a Cartesian product, so we're multiplying these guys together to create a new relation, and only select them where the department name is comp sci. So that's a bit more of your natural join operations. Two more things about natural join operations that are a bit different is that they're associative. So it doesn't matter which ones we put first because we're getting the Cartesian product, and they're commutative, so the order doesn't matter, similar to the associative one. Okay, so earlier if we did something like R intersect with S and then S intersect with R, sometimes you might get something that's a little bit different. So just be aware of that there, that for our join operations, for a natural join, it's associative and commutative. Great. So a data join is something a bit more unique from a natural join because it allows us to specify a condition on what to join on. So essentially joining up between two relations based on a condition between the two of them. And this data in the data join, so our data join S is equal to the Cartesian product of R and S, where the select of the data is provided to us. So this is a bit more complicated in algebraic terms, but essentially what we're saying is do a theta join on two relations based on a specification that I put between those two relations. So again, for instance here, we could say something where project theta join between instructor and department on the attributes, on the tuples where the instructor department name is equal to department name. Okay, so that's kind of the comparison between these two that we'll have. And again, natural join is more so just joining across all of the elements naturally, whereas a theta allows us to get more specific with what we want. So we can try to do a theta join between an instructor and teacher's relation, one that we have here. We have kind of a sub relation that we can look at. So it says select the relation instructor where the department name is equal to physics, and do a theta join to the relation teaches where the teaches the instructor.id is equal to the teacher's ID between these two relationships here. Okay, so this will kind of join them together based on this attribute. If we don't have this little select symbol, or sorry, this attribute down here, it's going to be a natural join. Okay, so essentially theta joins allow us to specify a condition that we would like to use. So we looked at the natural join and the theta join, and now we might look at these other things you might have heard of called the left to right join or an outer join as well. So these are 3 different types of joins. And the reason these are important is that they avoid loss of information. So we're going to compute the join and then adds tuple from one relation that does not match tuples in the other relation to result of the join. And the reason why, especially if we're looking back at our natural join example, these are a little bit more confusing looking because we do lose a bit of information sometimes here. For instance, we had a column where we joined on B with 4, but because we didn't have a similar 4 in both of our shared attributes of B and D, it won't be showing up here in our information. So that data is actually not in our next relation. And again, if we lose data, that's an issue for us, right? So we want to make sure that we're not losing any information that we have inside of our join operations. And the way that we could save these is by the use of null values. This means that it's, you might have heard of it as nil. There's just nothing in there, and it's just a placeholder for us to use it as well. One more thing noted here is that all comparisons involving null are roughly speaking false. So even though when we think about object-oriented programming, a none type is technically a type that we have, in this scenario, it can be synonymous to not existing. So we have our 2 relations here, relation instructor with the relation teaches, and this is going to be an outer join example. So an outer join here between our IDs, it looks like we have the same, at least 2 of the same IDs. And for these 2 ones down here, our Bio 101 and our Mozart name for a person, we're going to try to join them normally. So instructor and teachers will be joined. And it looks like we picked the IDs that were shared between the 2 of them, 101, 121. And it looks like we joined our Srinvasan and Wu individuals with that one. So we just got the 2 IDs, department names, and course IDs that existed, or excuse me, the IDs that existed in both. Now we could try to do a left outer join, right? So we could say instructor, this is kind of our bracket for left outer join. It's on the left side of our join symbol. And join that with our teaches. So we can go back here, and we know that 101 is in both of these. 121 is an ID in both of them. 151 and 767 are not in both of them there. So what can we put here? Well, we'll put in our regular joins on there. But what we're also going to do is grab that piece of data that wasn't caught in the join on our left side of our instructor, left outer join of our instructor relation, and we're going to toss a null in there, right? Now we don't lose this person. We just don't have a course ID that they're teaching. Likewise, if we do an instructor of a right outer join, we're going to take whatever was left over on the right side of our teaches here. We have our ID 101 and our 121, these 2 individuals still here. But if we look at our 767 from our previous one that was Bio 101, it looks like we never brought that over inside of our join, right? So instead of just removing that ID, we're going to go ahead and put null inside of the name department name and just fill in our course ID and our ID. Any attributes from our right side of our relations that we're joining is going to be brought in. And now finally for the full outer join, which is probably the most useful one that we have here, it's going to just take everything and combine it for us, right? So you're going to take up anything that's missing from the left side that didn't work in a join, anything that's missing from the right side relation, and just pull them in there, right? So we have these nulls inside of all these here. Okay, so these are these different types of joins, and I won't go, if I try reading this out loud, I might sound a little crazy, but essentially these are kind of the relational algebra that you could see inside of each of the joins. And what I want you to notice here is just where on the left side these nulls are actually happening here. We can see here that we're unioning anything null with anything inside of our S relation, so whatever's after the join sign. And then on this scenario here, we have our relation R, and we're getting a Cartesian product of everything that was null inside of that one too, okay? Finally, for our full outer join, it just combines both of them together. Our final type of join is more of a logical join that's not really offered inside of the SQL traditional languages here, but it's called the semi-join. And what this does is it returns rows from resulting schema R when there's one or more matches found. So a semi-join is essentially going to join on a predicate between relation R and S, and it's going to project all the attributes from our relation R that we're starting with onto S once it finds a match. So we can see here from our previous example, if we do a semi-join with instructor and teachers instead of our normal join, we're going to get back the ID of 101 from the first column here. We could see that the relation R is identical to our two columns here as well, but we also no longer go back, or no longer continue from there as well, because this is the only one that we saw since 2018 that worked for that join, okay? So here's the actual syntax for it again. So it's instructor, semi-join on the instructor ID and teacher's ID, and select where the year of 2017 is greater than, where year is greater than 2017 in the relation teaches. So a general idea of why we might want to use semi-join is that we're minimizing the amount of data we need to transfer. And essentially what we could do is try to, if we're working with large databases, stores some temporary semi-join information, temporary one, get a result from another join from original node, such as the S in our example back here, and then compute that result over them as well. What we said earlier, though, is that it's not typically used in our SQL environment, so you'll most likely be dealing with outer join, left join, and right join. But it's just good to be aware of these possibilities and how our relational algebra could work, especially if we're getting into more theoretical sides of these. When you want to maybe make a database system a bit more efficient, a semi-join might be an opportune, you might be able to code a way to use semi-joins more effectively.